Welcome to the world of gravitational fields. This is a rather short unit, so get yourself ready for a quest coming up very soon. Alright, so just a bit of background. You don't need to copy this down, but it's just a better appreciation of how we got to where we are today. Once upon a time, we thought that we lived in a geocentric universe. In other words, the Earth was at the center, and everything just orbited around it. A couple of centuries later, we thought that, hey, you know what, maybe it's off. Maybe it's the sun that's at the center of our solar system, and, the Earth is somewhere over here, and the moon orbits around the Earth. And, they thought about it and pondered over it. But there are others that said, hey, wait, what if it's the other way around? Let's say that the sun is in the middle, Earth has its orbit, and, if you look at night, sometimes you may see, Mars, Saturn, Jupiter, just out there in the skylight. And, maybe they orbit around the Earth. So they really haven't confirmed anything yet as of this date. All right. But yeah, if you are familiar with the story about Tycho Brahe, he had a protege under his belt, and his name was, where is he? There he is, Johannes Kepler. All right. And unfortunately, Brahe, he died after, I don't know if it was food poison or whatnot, but he went to a banquet and he died 11 days later. So Johannes took all his research, and he was able to prove that, we do actually live in a heliocentric solar system. Once again, that's a system where the sun is at the center and all the other planets orbit around it. And he discovered that through some interesting math, and that will be one of your homework activities for tonight, to go off and take his research and prove that, yes, the sun is in the center and everything else orbits around it based upon the calculated data. In fact, just something in a bit of history, they noticed this weird pattern happening in Mars. All right. So if you look into the stars appear to be stationary because they're really far away. But Mars, if you look at it every night, it seems to, follow ahead along with the Earth one night and then somehow move backwards before it moves forwards again. And that's known as the retrograde motion of Mars. And the only way that this can be explained is if Mars had a larger orbit than Earth. And we can demonstrate that with this lovely animation right over here. Okay, so again, the blue planet is Earth, the red planet is Mars, and we're looking at the position of Mars relative to the sky. All right, and at certain times during the year, when the animation restarts again, you'll see that again, Mars seems to lead, and then somehow pauses and goes backwards, which is the retrograde motion. And again, this can only be explained only if Mars had an orbit that's further away from Earth, and its orbital period was a lot longer. So Kepler was able to prove that, thus proving that, we probably do live in a system that looks more like this. And this is the magical formula that you're going to be deriving and figuring out what are the exponents over here that correlate the values together. One other thing to point out is that gravity hasn't been discovered yet in the timeline. All right, but they did create some really amazing devices. For example, this contraption over here, which can find out, the specific degree of a particular planet. It was so certain and precise that it was able to measure to the nearest 1/30th of a degree. That's kind of like having an angle of, let's say, 53.13 degrees, and your error is only plus minus 0.03 degrees. That's how precise this crazy machine was. All right, so they had some well-calibrated hardware to be able to collect their information and prove their research. Okay, with regards to physics in general, we know that we're bounded by 4 fundamental forces in nature. 2 of them exhibit at the atomic level, and the other 2 can be seen at least in our scale, all right, in the larger object scale. Just as a review, strong forces explain why protons somehow stick together in the nucleus of any given atom. For example, I don't know, let's just say helium. Right? Helium contains 2 protons and 2 neutrons. Now we know from back in grade 9 that like charges, they hate each other, so the protons should separate from each other. But you can imagine these protons as being rather fuzzy. Fuzzy as in they have this kind of virtual Velcro around them, and the Velcro makes them stick together. So as long as the protons are close enough together, they will bind, and that's what the strong nuclear force is. Of course, with larger structures, where the protons are much further away from each other because the nucleus is so rather huge, well, then the possibility of the protons being able to stick is a lot weaker, and there's another force that will pry them apart from one another. And that force that will pry them apart, especially when the nucleus is huge, is known as the weak nuclear force, and that explains nuclear decay. With regards to electromagnetic forces, I think some of us are used to, the bigger picture of magnetism and charges, how, again, opposite charges attract, like charges repel. But what is not as obvious are these two concepts here. All right. Yes, friction is an electromagnetic force because you do have two objects that are near each other. And as they're near each other, the protons and electrons from the two surfaces, well, they do like each other, and that's what causes them to stick together. All right. This is completely different than the world of traction, where the two objects deform each other and thus having a grip with each other. We're just talking about friction. Two smooth objects sliding on top of each other. Okay. And our main focus for today is this fourth force over here, the gravitational force. All right. As long as you have two objects with mass, they will inherently fall in love with each other. In fact, Isaac Newton was able to find that out, and I guess I'll get to that later on. One last thing just to point out on the slide over here is this last part over here. Gravity happens in all scales. In other words, even the relationship between protons and electrons, let's say, as the electron orbits around the nucleus, not only does it have an electric force, it also possesses this gravitational force of attraction with one another, and it should not be neglected. All right. So gravitational forces happen at the atomic level. It also happens in the celestial level as well. So, for example, the relationship between the sun and the earth, or even between different galaxies, there still is this inherent force of attraction in all scales. As for this infographic over here, it's just to remind you that your weight is really based upon not only the amount of matter that's contained in you, but it also has to do with the relationship between you and the distance you are from the Earth. RE is for the radius of the Earth. All right. So an average person may have a weight of about 1,000 newtons. But as you move further away from the surface of the Earth, your weight will quickly begin to diminish. Again, Isaac Newton noticed this, and he noticed that the relationship between your weight versus your radius was an inverse squared correlation. All right, so the further you were away from an object, your weight would decrease in a square or an inverse quadratic correlation. Sorry, an inverse square correlation. All right, so that's what he noticed, and that's what this infographic is just trying to point out. All right, and he said this over here, and that's what led to this very famous equation that you might have learned in grade 11. Fg is equal to something m over r squared. All right, there's an inherent attraction between two objects, which is the product of the two masses, and is inversely proportionate to the square of the separation between the two objects. The only thing that Isaac couldn't figure out is this mystery meat over here. He knew it was a very small constant, but unfortunately he passed away before we were able to discover it. Today we accept that constant as capital G, as a universal gravitational constant, and that number is 6.67 times 10 to the negative 11, followed by a bunch of units. Okay, so I'll talk about how we discovered that today. But before we get there, I just want to cover one more formula. All right, another one that we might have covered earlier on is Fg is equal to mg. So the weight of an object is equal to the mass times the gravitational field strength. But how do we determine this letter G, which is your gravitational field strength? Well, what you do is you just take these two equations and equate them. Right? So mg is equal to capital G, big M for the big object, little m for the little object, over r squared. Little objects divide each other out. So if you ever want to find out the value of G of any given planet, what you need is the universal gravitational constant, the mass of the planet, divided by the radius of the planet itself. So in other words, if you sub in the values for Earth, you'll get a value of G of 9.81 newtons per kilogram, which we know is also equal to 9.81 meters per second squared. So that's how we're able to determine the acceleration due to gravity of other planets, by knowing about the size of the planet, as well as the composition of what the planet is made up of. Because if you know the composition, well, back in grade 9, you learned that density is equal to mass over volume. So by the radius, you can eventually find out the volume of the planet, And by knowing the composition of the planet, you can figure out the approximate mass, or the density of the object. You can figure out the mass, and then you can sub it in and eventually find out the mass of the acceleration due to gravity of all different planets. All right, and that'll be one of your assignments for your homework. And here it is just animated out, the same effective thing. Okay, so how do we find out that capital letter G? Well, Henry Cavendish discovered it about 100 years after Isaac Newton's death. And he didn't discover it on his own. In fact, he bit off somebody else's experiment. There was another famous scientist called Charles Ampere that existed around his time as well, but he was doing a completely different experiment. He noticed that, yes, opposite charges will attract towards each other, but at what ratio? He noticed that it was this type of correlation. In other words, the product of the two masses divided by the radius squared multiplied by some crazy constant. Luckily for him, that constant was a big value. It was this number here, all right? Roughly 9 followed by 9 zeros. So it was a huge constant, and it was, fairly easy for him to determine it. And what he did was that, again, he placed opposite charges, and those opposite charges would allow the smaller charges to pivot and become attracted to it. And as it pivots, it generates something known as torque. So what Henry Cavendish did is that he supersized it to the size of a barn, and that's what this upper mechanism here is for. As the system is rotating, it causes this mass here to either go up or down, thus indicating the corresponding force due to the torque that's being twisted on the system over here. Then he'd place another mass around and cause the masses to attract towards each other. He'd move it further away, move it closer, double the size of the mass, and as he continuously did this, he noticed that the relationship of that resulted in a constant for this formula over here. What did he discover? Well, he discovered capital G as this value here, 6.75 times 10 to the negative 11. Compare that with today's answer, and holy smokes, that's pretty amazing that back almost 300 years ago, he was able to do this experiment successfully in a barn and only be about 1% off from today's accepted answer. That's pretty amazing. Another fancy word that we need to cover is the geosynchronous Earth orbit. If you recall back in grade 9, there was this lovely picture in your textbook. What it's trying to emphasize is that, again, each of these white dots represents a satellite that orbits around the Earth. All right, and you'll notice that there are a lot of them that orbit around in this location over here. And it's known as the geostationary Earth orbit. What it is that while you're on the Earth, you may notice that on your house, some of you guys might have satellite TV. And that satellite is pointed in a certain direction. All right, and once the technician sets it up, there's no motor to realign it afterwards. So in other words, it's expecting to have a satellite somewhere out there in deep space, pointing back towards it. Now, if that satellite is way too close to Earth, it has to orbit very quickly in order for it not to fall back to Earth. So it has to be really far away. In fact, if it's at a certain distance of, this number up here, far away from it, then it'll have the illusion of being stationary. Because remember that the Earth rotates once every 24 hours. So you need to have a satellite that's far away enough that it too will also have an orbital period of 24 hours. All right, and that way it's always in direct contact with your satellite at home, and you can always make that connection. Of course, that's different than GPS technology, because if you look at this picture again, you'll notice that there's a bunch of satellites that are very close to the Earth. And GPS operates under a different principle where it's not in a geostationary orbit. Instead, the satellites are on a very strategic path that looks something crazy like this. All right, so they orbit around the Earth many times in a given day, but they need to be closer because, as you may know, GPS technology, they can fit inside watches. So in other words, it needs to be able to be received by a much smaller antenna as opposed to that huge dish that you might have sticking outside of your house. All right, so the only way to accomplish that is to bring the satellite much closer to the receiver, which is in your cell phone or in your smartwatch. All right, but in doing so, it does move very quickly, and then Einstein's laws start to kick into play. All right, with regards to relativity, but we'll save that for a future adventure. As for now, let's just understand that in order for an object to orbit around the Earth, it must abide by this, right? Where the net centripetal acceleration is the force of gravity. So if we draw a free body diagram of the satellite itself relative to where the Earth is, it's the force of gravity that allows it to maintain its orbit around the Earth. All right, so your formula for your F net is just equal to Fg. We can expand that out right now. Why not? We know that F net centripetal is equal to MAC. And that's equal to the force of gravity at a long distance. All right, and that's why we need to use the big formula G, mass of big planet, mass of the tiny little object, over r squared. We'll quickly see that the masses of the little objects disappear, so we're left with this formula as a general starting footprint, I guess. All right, and with this, now we can sub in our centripetal acceleration equations that we learned in the previous unit. All right, so AC can either equal v squared over r, it could also equal 4 pi squared r over t squared, or it could also equal 4 pi squared r f squared. All right, and you'll sub the one that's appropriate based upon the problem that you're dealing with. For example, if you're trying to figure out how fast is it going in its orbital path, you probably want to use this formula here. If, for example, in the geostationary orbit, you know it takes 24 hours to orbit all the way around, you'll probably want to use this formula here, but just make sure that you convert your time in 24 hours into seconds before you sub it in. And if you're dealing with frequency, then obviously you use this when you sub it in. Okay, and I'm explaining all that right now because in the next PowerPoint slide, it's just a bunch of formulae. Okay, and I don't want you to be, absorbed by all these different equations over here and, God forbid, try to memorize all of them, because that's not the objective. Instead, the objective is understanding what's going on, and by using all the formulas that are written or shaded in blue, that you can derive all these other crazy equations that you're trying to look for in your homework. Okay, but before we get there, one last thing just to share with you, and it's just to better appreciate what's going on. It's that simulation that I have over here. Classic demonstration. All right. It takes a certain amount of energy for an object to orbit, and it takes even more energy for it to escape Earth's gravitational pull. For example, with this, we're just using arbitrary values. For example, 1 bag of gunpowder will result in an outcome of a projectile that will look like this. Okay, you'll see that it's attracted to the Earth's pull, and unfortunately it falls back to the Earth. If I increase and give it more kinetic energy, due to the release of chemical energy from the gunpowder, it might travel a further distance, but if you don't give it enough, unfortunately Earth's gravitational pull will pull it back down. So you need to give it just enough energy so that it's able to orbit. In fact, when any sort of satellite is orbiting around the Earth, it's constantly falling to the Earth. You can imagine that, for example, if it's right here, it's falling to the Earth over here, but by the time it falls, it's in a different position, such as right over here. So it starts to fall to the Earth, but it's yet in another position again, so you're constantly falling back to the Earth, and that's what orbiting really is. Now, let's try out 4 bags, because I just want to show you that orbital paths don't always have to be perfectly circular. It could also be in this weird elliptical path, where if the animation's right, it'll speed up as it gets closer to the Earth, and it'll slow down as it moves further away from the Earth. Sometimes scientists, they may use this as a gravitational slingshot in trying to accelerate satellites. All right, and you need to have enough energy so that the satellite can break free from Earth's gravitational pull and travel to infinity and beyond. That's a cool demo I want to show you, and hopefully you can use that to understand, what orbiting really is. Okay, you're trying to have just enough energy so that it can orbit in a perfect circular path around any sort of celestial object. And that's what we're trying to get at in today's lesson. Okay, here's your homework, and I'll catch you guys in the next episode.